Hello everyone. So far we have considered functional of the form that is given by integral from a to b capital F of x comma y prime dx that depend on x, y and y prime or more than one function. So we also consider in the last lessons a functional that depend on more than one unknown function. So that is given by integral from a to b f of x comma y prime, and then sorry, let me write it again. So that is y1 and then a y2 and so on. We have yi and we have also a dependence on first derivative. So y sub I prime dx, and we use the subscript I for, and I run from 1 to n. So that functional depend on several functions and their first derivative. However, there are many problems like in theory of elasticity where functional could depend on not only y and y prime but on higher derivatives, and thus it's worth to make the theory more general. And for simplicity we work with the single unknown function y of x and consider a functional that is given by j of y is equals to integral from a to b capital F of x y y prime dot 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 y subscript n superscript n for denoting the nth derivative of y. So this y superscript n denote the nth derivative, y prime denote the first derivative. So this is our functional. So our problem of interest is that among all the functions y of x which belongs to a class of a function given by d sub n a comma b. So we talked about d sub n of a comma b class where the function are basically lies in between a to b and which have continuous derivative till the nth derivative. The function whose nth derivative is continuous, nth and the lower derivative, and these functions satisfy the boundary condition given by, so let me write the boundary conditions. So boundary conditions. So we have a boundary condition that y of a is equals to a naught, y prime of a is equals to a1 and so on, and y n minus 1, the n minus 1th derivative of a is equals to a sub n minus 1, and similarly goes for the b. So at the point b we have y of b is equals to b naught, y prime of b is equals to b1 and so on, y n minus 1 b is equals to b sub n minus 1. So that are our boundary condition. We have two n boundary conditions. So find the functions for which above functional which given by the which depend on the first, second and so on n derivative has an extremum. So this is our problem of interest. So with this we use the same argument as before to find out the necessary condition to a extremum. So let the variation in function y of x is h of x. So our function change to y of x plus h of x, And next thing, that our functional j of y change to j of y plus h. Now h of x is such that the y of x plus h of x satisfy the same boundary condition, and for doing that it must satisfy the following boundary condition, that h of a and its higher derivatives are equals to 0 at these boundary points. Variation in functional is now given by, we denote it by delta j, which is equals to j y plus h minus j of y, and then I put the value of both of them. So first write the value of, let me use the another page. So this is integral from a to b. First I will write the value of j of y plus h, which is given by f of x comma y plus h comma y prime plus h prime, and so on, minus f of x comma y y prime, and so on till the yn, and then a dx. So that is our variation in our functional. Using the Taylor theorem, we can show that if you use the Taylor theorem to expand this, what we get is from b to a, and we are interested only in the first variation, which is delta j. So we write the first variation term, that is given by the following. So this is dot 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 plus f sub y n and h n, don't confuse with h and n, dx plus dot dot dot. And now this first term, so this term, which is the first variation in dx, another term will be higher order terms, we are interested only in the first order. So this is basically our del j, and the necessary condition for the extremum is that del j must vanish identically. So from there what we get is that integral b to a f sub y h plus so on plus f y sub n h n dx is equals to 0. And as an exercise, you can proceed as in earlier cases by integration by parts, and using the boundary condition of y and its higher derivative, we can show that this can reduce to the integral plus dot 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 plus minus 1 to the power dn over dx to the power n f y n h of x. This is h of x dx is equal to 0. So that's what we get, which is true for any h of x with n continuous derivative and which satisfy the boundary condition of h. And because it's true for all of hx, this integrand, which is this function f sub y minus d over dx and so on, must identically equals to 0. So our condition for each theorem is turned out to be the following. Is equals to 0, and which is called as before the Euler equation, which is a differential equation of order 2n, and its general equation contains 2n arbitrary constant which can be obtained by 2n boundary conditions. And one more remark that I want to emphasize, and I want to make it that is from the proof it seems like we have presupposed the existence of derivative, but it can be shown by some general argument that from the equation of this del j, which is given by the following, implies the Euler equation directly by a general argument. You can show that, but we will not do that. But it seems like we are presupposing the existence of f sub y double prime and f sub y triple prime and so on. These terms basically, let me write these terms. We are supposing the predeterminant. First we already determine that these are already existence, but this is not true. So I think we can stop here. So thanks for watching and see you in the next video.